Yes. So thank you very much for the invitation to come here. I have adjusted my talk ever so slightly based on some of the stuff earlier today and yesterday. So the first question is, why am I allowed to speak here today? So I grew up in Boston, and so we have a slightly distorted view, I think, of the geography of the world. So for us, where I live is actually part of the Mid-Atlantic.
What's the Gulf called on this map?
The Gulf of South Boston.
Oh,
I mean, really. And so I mentioned yesterday a more number theory game that I had come up with, the Zeckendorf game. This is just a link to a talk I gave on it if anybody's interested in pursuing this further. And the next slide has a subset of papers I've written over the years with my students. What I love about these problems is they are extremely accessible. When I'm training students for grad school, to send off to many of you, these are the problems that are not typically cared for by the senior researchers in the field, but in terms of a training ground, in terms of how to think creatively, these are absolutely wonderful. In addition to doing an in-person program, I'm here to recruit for the Polymath Junior program. And so we actually have funding for graduate students and professors who are interested in running groups with me. We are trying to provide experiences to as many people as possible. Several people mentioned the Gettysburg Mason Conference, which was right as the pandemic restrictions were coming in. That led to the creation of this online program. The goal was not to create a good program, and we succeeded. The goal was to create a program that could run very quickly and provide research opportunities to many students, as well as mentoring opportunities to many people. And it was so successful, we keep doing it every year. The number of people have grown, and so I am really looking for people to run groups with me. I have some money to actually provide compensation. If you're interested, let me know. The main talk I'm giving today is related to a problem that I want to study this summer, which means I cannot solve all of it right now, nor do I want you to solve it in the audience. This is more planting the flag of, I think there's going to be some interesting things to investigate. All right, so the first is to justify why I'm allowed to speak in a Mason talk, not just geographically, but subject content. How do we prove existence of things? Well, one of my favorite proofs is the reason something exists is we can show that there are infinitely many of them, therefore there must be at least one. And so if anybody knows a better proof than Dirichlet for the existence of at least one prime in arithmetic progression for arbitrary modulus, please let me know. I've heard from one of my colleagues that there is a way that works for everything. This is not, your facial expression is not being recorded, but that was my expression to him as well. I'd love to see, is there a way other than Dirichlet to prove that if I give you a general pair, A, B, M, relatively prime, there must be at least one prime congruent to A mod M. So if anybody knows that, I would love to see. There's at least several people here who have had similar experiences to me as teaching at one school and then going to another school where they have different philosophies on grading. I grew up with a 50% was a really good score. When I arrived at some schools, I will not name them, that led to students wanting to burn me either in effigy or in person for saying that they can't do mathematics because I gave them, a 40% and said, that's a great score. So one of the things you can do is you can decrease how many parts are worth a lot of points. So there's not that many points, but you can also put in some more softball questions. So I'm not sure if people are familiar with Telserid's theorem. What's nice is, unlike Dirichlet's theorem, there's actually no constraints on A and M. So if I give you any two integers, there are infinitely many composites congruent to A mod M. What's interesting is this is a great part of my philosophy. Try to get as much credit for everything you do. I ended up writing an article recently with two former students on how to create exam questions based on stuff like this. I hope you will not get bored during my talk. I understand I am the only thing preventing you from getting lunch or travel or cherry blossoms. But if you do get bored, there is at least one case of this that is non-trivial, which I encourage you to do. Okay, next proof, proof by parity. So because it's parity, I think I can justify talking about this in a number theory conference. This is the famous bridges of Königsberg problem. Can you travel across the different regions where you go through each bridge once and only once? And you very quickly see that the answer is no, because every vertex, when we make this association, has an odd index. And so you can lose two vertices for the start and the end, but every other time, once you go in, you have to go out. And because of the odd number, we know that there's no way to do it. So I love arguments where you can quickly prove that something either happens or doesn't happen. Unfortunately, they're not always constructive. Now, in this case, there's no way you're going to have a constructive path because no path exists. For other things, as you heard yesterday, my goal is, can we find a constructive way to do something? So I came up with a couple of years ago with the Sperner or the triangle game. And the way it's played as follows. On the far left, you can only label the vertices with a 0 or 2, the far right with 1s and 2s, and the bottoms with 0s and 1s. Any interior vertex you can label with a 0, 1, or 2. And your goal is to play defense and to prevent me from getting a triangle labeled 0, 1, and 2. If I can do that, I win. And so I've gone into elementary schools all the time and I've played this game, and I let them have a choice. If we alternate moves, it's going to be very easy for me to do this. I'll give you $100 if you can stop me. If you get 2 moves for every move I do, I'll give you 50. If you get 3 moves for every move I do, 25, and so on and so on and so on. When I was doing this to high school students, one of them asked, can we bank moves? And I go, oh my God, I never thought of that. And I act, this is where you have to act a little bit. It goes, oh, all right, I'll let you bank. Does anybody know the answer? I think at least one person, based on a book they showed me, knows the answer to this. Does anybody want to play me?
Oh, isn't it that there's always a 0, 1, 2 no matter what?
Yes. So the winning strategy is now the question of, what is my winning strategy? Do I have to be careful? What's the winning strategy? I'm sorry?
You just do arbitrary.
Yeah, just play. You can't screw it up. So we had a recruiting day at Williams, and I was teaching a problem-solving class, and I said, any student who beats me, I'll get you free admission to Williams. I'll pay everything. And so, boy, were the students excited. And so the strategy is very simple. This is actually related to a fixed point theorem. And an application of this fixed point theorem is to prove Nash equilibria exists. So this is not a game that has no importance. This is actually the key step in proving a fixed point theorem, which is used to do a lot of things. And so the main result is that if you were to play this game and look at how many 0, 1, 2 triangles you have, it turns out there's always an odd number. And since there's always an odd number, the smallest odd number you can have is 1. And so there must be at least 1. Oops. So the question is, how do we prove this? So as always, we start off with an easier game, and then we extend from that. So the simpler game is to play it in 1 dimension. So I start off with a line segment. Whoa. And I have a bunch of vertices that I have to fill in. I have a 0 at one end, I have a 1 at the other end, and I want to start putting in labels. And so I will let you do all the moves, and I won't do anything. And so when you start to analyze it, well, it's clear that you have to start labeling everything going from the 0 over with a 0, because as soon as you put in a 1, you lose. Similarly, when you start at the other end, you have to put in all 1s or you lose. So clearly, there's no way you can prevent me from getting a 0, 1 segment. So I like this proof. It means that I don't have to, that I know I'm going to win, even if you get all the moves, but it doesn't give us as much information. If we're willing to do a little bit more work, we can actually get that the number of 0, 1 segments is going to be odd. And up to symmetry, there's really only 3 possibilities. I really should also write the 1, 1 case, but the 1, 1 case is really the same as the 0, 0 case. And the 1, 0 is really the same as the 0, 1 case and whatnot. So there are 2 possibilities when I add something in here. If I add a 0, then I don't change the number of 0, 1 segments. If I add a 1, I increase the number of 0, 1 segments by 2. If I put a 1 here, there's no change. If I put in, and if I put in a 0, there's no change. So the parity of the number of 0, 1 segments only changes, never changes. If it starts off as odd, and it does because we have just the 0 and 1 labeled, it stays odd throughout. So I know there's an odd number of segments. So in the first proof, it's possible that I might lose if I play poorly. But now we know that there's no danger at all. This is just writing it up nicely. So let's quickly prove that the Sperner's triangle game is a boring game. So what we're going to do is we're going to count the number of 0, 1 segments. And how can we get a 0, 1 segment? Well, we could get it from a triangle that is labeled 0, 1, 2. We could get it from a triangle that's labeled 0, 1, 1, or we could get it from a triangle labeled 0, 0, 1. No other triangles, I'm hoping, have a 0, 1 segment. Okay, I'm hoping the notation is obvious. So how many segments of 0, 1 does this give? Each one gives 1. And these two give 2. So if I only care about the parity of the number of 0, 1 segments, I know the 0, 1, 1 and the 0, 0, 1 triangles, they're not going to change the parity. So the parity is going to come down to how many 0, 1, 2 triangles do I have? I know from the one-dimensional case, we have an odd number on the bottom. So we have an odd number of 0, 1 segments on the bottom. But if you look at the interior, every 0, 1 segment in the interior is counted twice. So all interior counted twice. Therefore, we have an odd number of 0, 1 segments. And so because T0, 1, 2 controls the number of the parity of the number of 0, 1 segments we have, if we have an odd number of 0, 1 segments, we have to have an odd number of 0, 1, 2 triangles. Therefore, there has to be at least one. Therefore, the game is rigged and I'm going to win. All right, so now it's time for audience participation. So help me with my summer program. Any thoughts about projects worth studying? I've got a list on the next page.
0, 1, 2, 3. What about
Good, higher dimensions, right? Are you the, okay. There was somebody who was wearing a shirt about, P reasons or in back, why it's better. And you did it for an arbitrary P. And then you said, I think P equals 7. Right. But yeah, do this in higher dimensions. And what happens? What else? Different shapes. Maybe even a torus. Where you wrap around. And then if you do something like a square, we have 0, 1, 2, 3. Now it gets interesting because now you might not actually be forced to have all the different labels. Any other thoughts?
polygon, go inside?
And again, anybody who wants to, collaborate, please just shoot me an email.
Instead of labeling vertices, you label edges or faces.
Okay. Good. Label edges or faces. And so none of you mentioned the main generalization I was going to look at, which is why I chose to do the slides in this order. Please. Oh, so we keep the triangle, but you have more possible. Okay.
Also, one guess, you label everything with like real numbers from an interval, but then you're trying to, one person is trying to minimize some like maximum of a fixed function over each triangle, and another person's trying to maximize that function.
Okay, real labels, you're gonna have to email me. Maximize function. I am fine with the game no longer being playable for kindergartens. It is okay to have games at different levels. I do a lot of sports statistics. Any football fans here?
Washington area, you gotta
Say football, not
year.
football. And so, there's the ranking called the quarterback ranking, which everybody knows 100 or better is great. But if you actually ask people to describe the formula, it involves the following things. I don't know how it's pieced together. So for something like this, that's a little bit more complicated, happy to consider something like that. One of the things I love about the initial version of the game is I can do this with young kids and get them involved, get them thinking. Some of the stuff we already had, but the other one is to try to make the game fair. And so we know that there has to be at least one 0, 1, 2 triangle. What if we subtract that? And what if we have a competition? I get a point every time there's a 0, 1, 2 triangle. You get a point every time there isn't. Is there a strategy in a situation like that? And so what we can do is for the different shapes, we can calculate the expected number. If it's just a one-dimensional game, we can calculate what's the expected number of 0, 0 segments, or maybe 1, 1 segments versus 0, 1 and 1, 0 segments. And you can play this in higher dimensions as well. Are there constructive strategies to win, to beat the expected value? And so one of the things that's going to really help is the linearity of expectation or mean. So I've deliberately not done the calculation. But you can easily calculate this. You can calculate the variance. It's not going to be too hard to calculate the covariances. We will have lots of students on this. They can calculate stuff like this. And then you can start maybe making points depending on how far away you are maybe from the mean, with the variance and standard deviation being a natural scale. I just wanted to mention, just because a lot of people have been talking about coding, this is one of my favorite coding tricks. If I want to quickly see if I have a triangle with 3 different labels, I use as my labels 2, 3, and 5, and then just see is the product of the labels a multiple of 2 times 3 times 5. If you don't like primes, which is really bad for this audience, you could instead use 1, 10, and 100 as your labels and see if your sum is 111. So if you don't like multiplying, you can always do a little trick like that. And so, one question is, and given that we're running a little bit late, I'm not going to go into this, but is to try to come up with some strategies. So for instance, if somebody has put a 0 here, we're going to red just to make it a little bit more easy. If I'm trying to get 0, 1 segments, where do I want to go? What's a good place for me? I mean, I could go right next to it and guarantee myself something like that. Is it better to go off a little bit, maybe off even further? And are there natural strategies you can do where you're going to leave things in to be filled in later, which you will be able to get, but you don't have to use a move right now. So there's a lot of strategy games like that. So I think this is going to be a really good project for students because there's lots of different ways we can extend. And so again, thank you very much for the invitation. Extra credit if anybody can figure out what the image on the left is. I did rent a car, so I will be going to see the cherry blossoms later today. If anybody wants a ride, please let me know. And thank you again.